There's a moment in every significant scientific event when the data stops being data and starts being something else entirely, something that makes the people holding it go quiet. Not the quiet of confusion, the quiet of people who understand exactly what they're looking at and aren't sure they should say it out loud. That moment happened on the morning of October 29th, 2025. And what followed in the hours, days, and weeks after that morning hasn't been fully explained. Not by the agencies that tracked it, not by the institutions that analyzed it, not by the researchers who are still, right now, working through the implications of what they recorded. Here's where we need to start. Not with the discovery, not with the press releases, not with the careful language scientists use when they want to communicate alarm without saying the word alarm. We need to start with a principle you already know, but may not have thought about this way. When something moves through space, it follows rules. Not guidelines, not suggestions, rules enforced by gravity and momentum and the unchanging physics of vacuum. A rock thrown into the void will keep traveling in a straight line until something pulls or pushes it otherwise. A comet falls toward a star, accelerates as gravity tightens its grip, swings around closest approach, then climbs back out along a mirror image path. The math is simple. The behavior is predictable. This is not a mystery. Celestial mechanics has been solved for centuries, and we've gotten extraordinarily good at using it. We can calculate where a comet will be years before it arrives. We can model its brightness, its outgassing, its rotation state. Natural objects do not surprise us anymore, not at the fundamental level, not in the ways that matter. What makes 3I Atlas different, what makes it something other scientists don't quite have language for yet, is that it didn't follow the rules at the moment when it was most important. It didn't follow the rules during the single window when no human eye, no orbiting instrument, no ground-based telescope could watch. And when we got our first look at what had changed, the data came back not ambiguous, but sharp. Not hinting at something strange, but presenting it directly, without apology, in numbers that were impossible to argue with. The people who first saw that data didn't speak for a while. Then they started making phone calls. Hold that in mind as we go back to the beginning, because the story of 3I Atlas starts long before October 29th, and the details from those earlier months matter more than most accounts have acknowledged. The object was discovered in July of 2025. Its initial detection came through routine sky survey data, the kind of automated scanning that modern observatories run continuously, cataloging thousands of faint moving points of light every single night. Most of those detections are mundane. Asteroids we've seen before, comets on familiar return trajectories, background noise in the catalog. When 3I Atlas appeared in that data, it flagged for one specific reason: its velocity. Not because it was moving fast in an absolute sense, though it was moving extraordinarily fast by any standard. It flagged because of how it was moving relative to the solar system as a whole. The object wasn't orbiting, it was passing through. Orbital velocity tells you everything about where something came from. Objects gravitationally bound to our sun move in predictable ways. Their speeds follow Kepler's laws. They trace ellipses. Their entire journey is a closed loop that will eventually bring them back. When something appears moving too fast to be bound, when its trajectory is hyperbolic rather than elliptical, you are looking at an interstellar visitor, something that did not originate in our solar system. Something that formed around another star, or in the space between stars, or somewhere else entirely, and has been traveling through the galaxy for an immense period of time before its path intersected ours. At the time of discovery, this was already extraordinary. The first confirmed interstellar object detected in our solar system had been Oumuamua in 2017, that elongated, tumbling mystery that accelerated unexpectedly and sparked years of debate. The second was Borisov, a comet that behaved more conventionally. 3I Atlas was the third, and it arrived with a profile that immediately distinguished it from its predecessors. The name carries meaning. The 3I designation, the third interstellar object, was assigned quickly, almost automatically, following established naming protocols. The Atlas component came through the standard process by which newly discovered objects receive labels. But there was something fitting in it, though no one designed it this way. Atlas in mythology was the figure condemned to hold up the sky, to bear something enormous, something above and beyond normal weight, alone. That resonance would become uncomfortable as the weeks passed. For the first several months of its tracked trajectory, 3I Atlas behaved more or less as an interstellar comet should. It had a nucleus, a solid body, irregular in shape, estimated between 5 and 20 kilometers across, depending on assumptions about its surface reflectivity. It had a coma developing around it as it warmed approaching the sun, gases sublimating off volatile ices and expanding into a diffuse envelope. It had a tail beginning to form, solar wind and radiation pressure pushing that outgassed material into the streaming structure that gives comets their visible appearance. These are normal things, expected things. The models built for it weren't wildly different from models built for any other icy body making its perihelion passage. What the models didn't account for, what no model could have accounted for, because no model had ever needed to, was what would happen at the moment of closest approach to the sun. This is where we need to talk about something called the Oberth effect, because it's going to be important, and the implications of it are stranger than they might initially appear. The Oberth effect is a principle in orbital mechanics that describes how the efficiency of propulsion changes depending on where in a gravitational field you fire your engines. When you are deep in a gravity well, moving at maximum velocity, every unit of thrust you apply produces a disproportionately large change in your trajectory compared to what that same thrust would accomplish in open space. The math is not complicated, but the implications are counterintuitive. The deeper in the gravity well, the faster you're already moving, the more amplified your propulsion becomes. This is why spacecraft bound for the outer solar system often fire their engines near Earth, rather than waiting until they're already en route. The gravity well boost multiplies the effect. This is why, if you were engineering a mission to deliver something to an inner solar system target and you wanted maximum efficiency, you would plan your release event for perihelion, the exact moment of closest approach. The exact moment of maximum speed in the gravity well. Not before, not after. Exactly then. This is what aerospace engineers call optimal. This is what mission planners call elegant. This is what 3I Atlas apparently did. But let's not get ahead of what we can demonstrate yet. At the time of perihelion on October 29th, observation was impossible. This is not a conspiracy, it's geometry. The object's trajectory carried it behind the sun from Earth's perspective in late October, a phenomenon called solar conjunction, and anyone who did the math back in July when the object was first discovered could have circled that date on a calendar. No telescope on Earth could peer through the sun. No satellite in orbit around Earth was positioned to see around it. The Parker Solar Probe, NASA's sun-grazing spacecraft that operates in the innermost region of the solar system studying the corona, was nearby but not positioned to image the object directly. The one instrument that had any chance of observing 3I Atlas at perihelion was the European Space Agency's JUICE mission, the Jupiter Icy Moons Explorer, a spacecraft designed to study Ganymede, Europa, and Callisto. At the time of perihelion, JUICE was 64 million kilometers away, far from its primary mission objectives, but geometrically positioned to catch at least an oblique view. Mission controllers made the decision to temporarily redirect its instruments. Whatever data they could collect from this critical moment was worth interrupting the normal scientific program. It was a reasonable call. The data they got back changed the nature of the entire event. 11 hours after perihelion, the first data packets from JUICE reached Earth and were processed by a team in Darmstadt, Germany. The processing was routine at first: calibration corrections, noise reduction, standard pipeline procedures. Then the numbers started coming out, and people began looking at each other across workstations in ways that don't appear in official reports, but that anyone who has worked in a scientific facility during an anomalous result will recognize. The brightness was wrong. Not slightly wrong, significantly, measurably, uncomfortably wrong. Models had predicted 3I Atlas at perihelion would reach magnitude 11.5, well below naked eye visibility, but detectable by modest telescopes. JUICE photometry returned magnitude 10.1. That's not a small discrepancy. On the astronomical magnitude scale, which runs counterintuitively backwards with lower numbers indicating brighter objects, the difference between 11.5 and 10.1 represents approximately 2.5 times greater brightness than predicted. comets do sometimes exceed brightness predictions. Volatile ices, when exposed to intense solar radiation, can sublimate faster than models expect, releasing carbon dioxide, carbon monoxide, and water vapor in bursts that temporarily amplify the coma's reflectivity. This happens. It is known. It has explanations. So the brightness excess alone, while notable, was not the thing that made people go quiet in Darmstadt that evening. It was what the distribution of that brightness revealed. Natural comets, even unpredictable ones, even ones that outperform their models, develop roughly spherical comas. Sometimes elongated by solar wind into teardrop shapes, sometimes irregular from asymmetric outgassing, but always centered on the nucleus, always diffuse at the edges, always following the physics of gas expanding into vacuum from a central source. What Dewey's imaging showed did not look like that. Around the central body, the nucleus still present, still intact, still on its predicted trajectory, there were additional bright points. Not diffuse regions, not elongated streamers. Discrete, distinct, separate luminous objects. 7 of them, each exhibiting its own spectral signature, each showing its own pattern of emissions different from the nucleus and from each other. 7 objects where there had been one. 7 sources of light arranged around the central body in a configuration JUICE observed for 42 continuous minutes. Here's the part that stops the conversation. During those 42 minutes, the bright spots moved. That by itself is unremarkable. Everything in space moves, but they didn't move the way ejected cometary material moves. Material blasted off a comet by outgassing or sublimation follows ballistic trajectories. It leaves the nucleus with initial velocity and then coasts, subject only to solar wind and radiation pressure. It does not accelerate. There is no mechanism in known comet physics to cause material to accelerate after ejection. Yet across JUICE's 4-2-minute observation window, these 7 objects were not coasting. They were changing velocity, not decelerating from some initial burst accelerating. Moving faster at the end of the observation than at the beginning, each following its own distinct trajectory, each diverging from the others in ways consistent not with explosive dispersal, but with controlled separation. This is not how natural objects behave. Natural processes do not accelerate material in vacuum after it has already been released from a parent body. Solar wind and radiation pressure produce forces, yes, but those forces are gentle, consistent, and unable to cause sudden velocity changes on objects of the size. Dewey's brightness calculations suggested approximately the size of a terrestrial school bus based on distance and luminosity. What accelerates in the controlled, variable, directional way JUICE observed is propulsion, engines, thrust being applied deliberately by something capable of deliberately applying it. The initial report from Dewey's data was classified within hours. This is not unusual for sensitive findings. The classification wasn't about suppression, it was about verification. Data that appears to show something extraordinary needs to be checked before it's released, because extraordinary errors are as possible as extraordinary events, and announcing the impossible only to retract it is damaging in ways that cascade. But the report went to the International Asteroid Warning Network, the coordinating body for global response to potentially hazardous objects, and from there, the machinery of global astronomical emergency response began moving. By the evening of October 29th, 36 observatories across 4 continents had been alerted. Emergency observation protocols were activated. Every telescope capable of angling toward the solar region surrounding perihelion was retasked from whatever it had been doing to this single problem. The community understood, without anyone having to say it explicitly, that something unusual had happened, and the next observation window, when 3I, Atlas, and whatever had come from it would emerge from behind the sun, needed to be covered completely. While those preparations were being made, another piece of data arrived from an entirely different source. This one was more difficult to process in every sense of the word. The Parker Solar Probe, while not positioned to image 3I Atlas directly, carries instruments designed to measure the electromagnetic environment of the inner solar system radio emissions, particle densities, magnetic field fluctuations, all the complex physics of the region near the sun. During the perihelion passage window, Parker's instruments detected a series of radio bursts. Not from the Sun, whose radio signature is well characterized and easily distinguished. From the direction of 3I Atlas, these bursts were centered at a very specific frequency, 1.42 gigahertz, the hydrogen line. This frequency is worth pausing on, because its significance is both scientific and deeply strange in context. Hydrogen is the most abundant element in the universe. At 1.42 gigahertz, neutral hydrogen atoms emit a natural radio signal, one of the most fundamental electromagnetic signatures in the cosmos. Radio astronomers have studied it for decades to map the distribution of hydrogen in our galaxy and others. And researchers searching for evidence of extraterrestrial intelligence have monitored this frequency with particular attention since the 1950s, when the logic was articulated clearly for the first time. If any technological civilization anywhere in the universe wanted to broadcast its existence in a way that another technological civilization would recognize as a deliberate choice, transmitting at the hydrogen line frequency would be a reasonable signal. It's a universal constant. It's easy to identify. It says, without words, that the sender knows something about atomic physics. Parker's instruments didn't pick up a continuous signal at this frequency. They recorded bursts. Rhythmic pattern bursts. The duration of each burst, and the silence between them, followed a sequence that researchers immediately recognized because it appears everywhere in nature, in growth patterns, in geometry, in the spiral structures of galaxies and seashells and plant growth. The Fibonacci sequence, 3 seconds, then 5, then 8, then 13, then 21, then 34, then 55, then 89. Each number the sum of the two before it. Each pulse lasting exactly as long as its numerical value in seconds. The pattern continuing without deviation. The Fibonacci sequence appears throughout nature. This is true. It is not mysterious in the sense of being unexplained. There are mathematical reasons it emerges in biological growth and physical processes. Its appearance alone, in some contexts, proves nothing. But here is the problem. The Fibonacci sequence does not appear spontaneously in radio emissions. Solar flares produce radio bursts. Plasma interactions in stellar atmospheres produce radio noise. None of those processes count. None of them maintain memory of prior values and calculate successive terms. The Fibonacci sequence at 1.42 gigahertz, broadcast in precisely timed pulses at the exact moment of perihelion, is not a natural phenomenon. Natural processes can create repeating patterns. They cannot create arithmetic sequences that require each emission to know what came before and calculate what follows. That is not physics. That is information. That is signal structure. And signal structure implies intent. The Parker data was immediately forwarded to the SETI Institute, to the Galileo Project, and to research teams around the world already watching 3I Atlas with ascending levels of concern. November 1st, 2025. The European Southern Observatory's Very Large Telescope in Chile had been ready and waiting. When 3I Atlas emerged from behind the Sun, the VLT, one of the most powerful ground-based optical instruments on Earth, acquired it within the first observation window and confirmed everything JUICE had recorded with what one internal communication described as devastating clarity. The main body, the nucleus, was intact, still on its predicted trajectory, still following its hyperbolic path through the solar system, still appearing in every observable respect like a comet making its perihelion passage. Surrounding it, now spread much further apart than JUICE's initial observation had shown, were 7 distinct objects, each on its own separate trajectory, each having moved considerably from where JUICE had seen them 50 hours earlier. This is where the orbital calculations became urgent. Determining the trajectory of any moving object in space requires multiple observations over time. You measure position, measure again, calculate velocity from the change in position, then project that velocity forward to predict where the object will be. It requires at least 2 data points separated by enough time that the numbers don't drown in measurement uncertainty. By November 1st, analysts had JUICE's original observation, 42 minutes of data from perihelion, and the VLT's acquisition data from emergence. That was enough to calculate rough trajectories for each probe. The calculations were run multiple times by multiple independent groups because the results were the kind of numbers people check twice and then check again. 3 of the 7 objects, probes 1, 2, and 3 by the designations that were quickly assigned, were not following paths that would carry them out of the solar system. 3 of the 7 had executed course changes that bent their trajectories inward. And the projections of those trajectories forward in time converged on the same destination. Not exactly the same point in space, the 3 probes weren't aimed at a single coordinate, but the same region. The inner solar system, Earth's neighborhood. Projected closest approach date, December 19th, 2025. 50 days from the moment of discovery. The numbers were checked, rechecked, and checked again. Not because analysts doubted the math, but because the math had implications that required certainty before anyone said them aloud. Probe 1's closest approach, 8.7 million kilometers. Probe 2, 9.2 million kilometers. Probe 3, approximately 10.1 million kilometers with larger uncertainty. To calibrate those distances, consider that the Moon is roughly 384,000 kilometers from Earth. Probe 1 would pass at roughly 22 times the Earth-Moon distance, less than a 15th of the distance to the Sun. In astronomical terms, this is not just a near miss. This is a visitation. This is an arrival in Earth's immediate cosmic neighborhood by objects that, based on everything observable about them, did not originate in this solar system, do not follow natural physical behavior, and had executed precisely calculated maneuvers at the optimal moment in their trajectory to direct themselves toward our planet. Each probe, based on brightness and distance calculations, measured at least 30 meters across. Larger than any satellite humanity has ever launched into orbit. Larger than individual modules of the International Space Station. And none of them were tumbling randomly, the way debris tumbles. They showed controlled, stable orientations, what aerospace engineers call 3-axis attitude control, the kind of stabilization system used in advanced spacecraft to maintain pointing accuracy. Their brightness varied periodically, and the period of that variation was significant. 16.2 hours, the same rotation period exhibited by 3I Atlas itself. Whatever had separated from the mothership appeared to have maintained rotational synchronization with the body that released them, even after separation. This was not spontaneous. It was not accidental. And by November 2nd, there was sufficient convergence of data from enough independent observatories using enough different instruments and methodologies that the phrase natural comet no longer applied to what was approaching Earth. On November 2nd, the International Asteroid Warning Network convened its first emergency session since its founding. Representatives from NASA, ESA, Roscosmos, JAXA, CNSA, and every major space agency participated, along with astronomical societies from 37 countries. The meeting was officially closed. The agenda leaked within hours, as these things always do. The items on that agenda were straightforward in language and staggering in implication. Confirm trajectories of all 7 objects, assess the probability of natural versus artificial origin, determine Earth impact risk, establish communication protocols, authorize defensive measures. That last item generated the most attention when it appeared in the open. The phrase defensive measures is deliberately ambiguous. It can mean enhanced tracking. It can mean contingency planning for deflection. And it can mean, when the object in question is not understood and cannot be safely categorized, considering options that cannot be retrieved once taken. Options that would eliminate the thing approaching before anyone fully understood what it was. There was an immediate and obvious problem with that logic, and it was articulated clearly enough in subsequent discussions that it became the counterweight to every defensive impulse. If these probes represented the first confirmed contact with extraterrestrial technology, and by November 2nd, most of the people in that meeting privately believed that's what they were looking at, destroying them would be the first thing humanity communicated to whatever sent them. And humanity would be communicating it not in words or mathematics or careful diplomatic language, but in a flash of light visible across the inner solar system. The message would be, "We saw you coming, and we destroyed you before you arrived." Whatever inference the sending civilization drew from that action would happen without any further input from Earth. Whatever response followed would be based on that single data point about what kind of species inhabits this planet. This is the paradox that kept surfacing in every policy discussion that followed. Adequate caution demands preparing for worst cases. Adequate intelligence demands recognizing that some worst-case preparations might constitute the worst case. The two imperatives do not resolve cleanly. They sit in tension with each other, and that tension has not been resolved by the time the probes arrived. What happened in the weeks immediately following that emergency session involved a kind of parallel processing that has never quite been publicly acknowledged. Official channels, the coordinated observatory networks, the formal ION working groups, the peer-reviewed analysis pipelines proceeded methodically. Data was collected, verified, published in carefully worded technical reports that consistently used language like anomalous behavior inconsistent with known natural processes, rather than the phrases that were circulating in informal conversations. Meanwhile, military and intelligence agencies in multiple countries were running their own parallel analysis, drawing their own conclusions, and making preparations that existed in a separate compartment from the civilian scientific response. The United States Space Force quietly began activating satellite tracking networks. Ground-based radar installations were recalibrated. In facilities that are not discussed in press releases, engineers ran simulations asking a specific question: if humanity needed to intercept an object on the trajectory Probe 1 was following, could existing launch infrastructure reach it in time? And if it did reach it, what then? These simulations were not, as of the information available, followed by actual launch preparations, but they were run. The fact that they were run tells you something about how the people with access to the full dataset were interpreting it behind the language of official caution. While governments assessed options and observatories gathered data, a quieter question was being asked by researchers who track the deeper history of unexplained signals from space. The trajectory back calculation for 3I Atlas running its path backward in time, accounting for galactic rotation and stellar motions and gravitational influences from known bodies, placed its origin point near the galactic center. Not precisely, because the uncertainties over interstellar distances and billion-year timescales accumulate beyond the resolution of any calculation. But the general direction was consistent. The dense central region of the Milky Way, the violent, crowded neighborhood surrounding Sagittarius A*, the supermassive black hole at our galaxy's core that contains roughly 4 million times the mass of our Sun, 26,000 light-years away. A region where stars crowd together with separations measured in light days rather than light years, where extreme gravitational environments and high-energy processes produce conditions nothing like the quiet suburban arm of the galaxy where Earth orbits. From that direction, from that specific part of the sky, this detail connected to something that had been sitting in the astronomical record since August 15, 1977. The Big Ear radio telescope in Ohio was running a routine sky survey that night, recording data to magnetic tape for later analysis. The next day, a volunteer astronomer named Jerry Eman was reviewing printouts of the previous night's data when a sequence of numbers caught his eye. The values represented signal strength on a scale from 0 to 9, then the letters of the alphabet for 10 and above. What Eman saw printed on the paper was 6 EQJ5, a sharp spike in signal intensity lasting exactly 72 seconds, centered at 1.42 GHz, the hydrogen line, arriving from the direction of the constellation Sagittarius. He circled it on the printout and wrote one word in the margin: wow. That annotation gave it a name that has endured for nearly 50 years, the WOW signal, the most compelling candidate for an extraterrestrial radio transmission in the history of SETI research. It was never heard again. Follow-up observations of that patch of sky, and there have been many, using increasingly sensitive instruments, have produced nothing. No repetition, no confirmation, no second data point that would allow the signal to be traced to a source and definitively categorized. It remains unexplained. Now consider, 3I Atlas arrives from the direction of Sagittarius. It carries, or releases at perihelion, objects that transmit at 1.42 GHz in patterns that require mathematical memory to produce. The WOW signal preceded this arrival by 48 years. The galactic center occupies roughly 1% of the sky as seen from Earth. Two independent anomalies, both involving the hydrogen line frequency, both associated with the direction of Sagittarius, separated by half a century. The probability of two unrelated events both pointing to that 1% of the sky by chance is 1 in 10,000. Add the frequency correspondence, and you are in territory where coincidence as an explanation requires more faith than correlation. Some researchers have proposed that the WOW signal was not a random broadcast, but a specific announcement, a hailing frequency transmitted ahead of an incoming mission, providing notice in the way that an advanced civilization might if it wanted to give a destination civilization sufficient time to observe the signal, understand its origin, and prepare for arrival. 48 years between signal and arrival sounds long by human standards. For something that crossed interstellar space at the speeds 3I Atlas traveled, for a civilization that thinks in timescales corresponding to those distances, that gap might be standard procedure. You send the signal. You send the mission. You wait to see if the inhabitants noticed, and if they demonstrate mathematical awareness of what was sent. The Fibonacci sequence at perihelion might be the same signal in a different medium transmitted not across light years in advance, but directly from the arriving vehicle, confirming the connection, establishing the reference frame. This becomes important later. Remember it. 7 probes, 7 distinct trajectories, 7 different destinations inside a single solar system, each assigned with a precision that implied not guesswork, but foreknowledge. This is where the story shifts from extraordinary to something harder to categorize, because what the orbital calculations revealed about these objects wasn't just that they were heading somewhere specific. It was that each was heading somewhere different, that the 7 destinations collectively covered the inner solar system like a survey grid, and that the fuel requirements implied by their observed deceleration profiles pointed toward propulsion technology that does not exist in any human engineering program, classified or otherwise. This matters more than almost any other detail, and it hasn't been explained away. The physics is not ambiguous. The implications of the physics are not ambiguous. And yet the full picture of what these 7 objects were doing, where each one was going, what each one's behavior suggested about its specific purpose, has not been assembled in one place in any public account that gives it the weight it deserves. Start with Probe 1, the largest, the brightest, the one that most directly announced itself. It was Probe 1 that the Very Large Array in New Mexico acquired on November 7th, 9 days after perihelion, when it transmitted for the first time. The detection happened at 2:37 Universal Time. A burst of narrowband emission centered at 1.42 gigahertz, lasting 3.14 seconds, followed by 5.08 seconds of silence, then another burst 8.04 seconds long, then 13.1 seconds of silence. 3, 5, 8, 13 the Fibonacci sequence again, now transmitted not from the vicinity of the parent body at perihelion, but from Probe 1 itself, weeks later, as it moved through the inner solar system. The sequence continued for 26 minutes before stopping. Total silence afterward, for days. Then on November 11th, another transmission. Same frequency, same Fibonacci timing structure. But within each burst, something additional was present. The signal wasn't just pulsing at Fibonacci intervals. The content of each pulse was modulated. The strength and frequency of the signal varied within each burst in patterns that weren't random noise and weren't natural electromagnetic variation. Information was encoded inside the structure. Probe 1 was not just announcing its presence, it was saying something. Dr. Rachel Kim at the SETI Institute leads the team analyzing those transmissions, and her situation is one of the most genuinely difficult in the history of her field. She's trying to decode a message without a shared language, without a Rosetta Stone, without any prior communication that would let her establish even the most basic correspondences. She knows the transmission is intentional. She knows it carries structure. She knows structure implies meaning. What she doesn't know, what nobody knows, is what the encoding scheme is, what base system the sender uses, what assumptions about mathematics and information representation have been built into the signal's architecture. Her team has tried everything available to them. treating the modulation as amplitude encoding, then frequency encoding, then phase encoding. Searching the signal for prime numbers, mathematical constants, geometric ratios. Testing whether the variations might represent a one-dimensional data stream that, when folded into 2 dimensions at the right width, produces an image. Nothing has worked definitively. Everything works partially, producing results that look almost meaningful patterns that appear almost coherent, structures that seem almost intentional but never fully resolve into clear, interpretable content. It's like receiving a letter written in an alphabet that contains all the same shapes as your own, but assigns them to entirely different sounds. You can see its language, you cannot read it. Kim has described this experience in internal communications with a phrase that stays with you. It's like being shown a proof you can tell is correct without being able to follow the steps. The underlying logic is there. The specific implementation is opaque. Her latest working hypothesis treats the transmissions as pedagogical as an attempt by Probe 1 to teach its encoding scheme rather than simply use it. The Fibonacci sequence itself, she argues, might be lesson 1, establishing that both parties share knowledge of this mathematical pattern, providing a reference point, a common ground. Subsequent transmissions might be building on that foundation, introducing additional elements of a shared vocabulary one piece at a time, patient, methodical, designed for an audience that is capable of learning but hasn't been taught yet. If that's correct, the timeline matters enormously. Each transmission adds a small increment of shared vocabulary. Building enough common ground for meaningful content exchange requires time, and time was the resource most constrained by Probe 1's trajectory. It would reach closest approach on December 19th. Whatever communication was possible had to happen before that date. After it, the probe would be moving away, signals weakening, the window closing. This is where we need to talk about the velocity, because the velocity of Probe 1 contains a detail that wasn't initially obvious, and that, once recognized, changed how analysts understood the entire mission profile. When first tracked, Probe 1 was moving at approximately 45 kilometers per second relative to the Sun fast by any terrestrial standard, but dramatically slower than 3I Atlas itself, which had been measured at roughly 61 kilometers per second at discovery. The probes had already shed enormous velocity through propulsion before anyone detected them individually. But here's what the ongoing tracking revealed. Probe 1 wasn't maintaining that velocity. It was still decelerating. Not all at once, not at constant thrust, but in a variable pattern, accelerating the deceleration slightly, then easing off, then applying thrust again that suggested active guidance, rather than a burn-to-depletion engine running down. Dr. Margaret Hilongo at NASA's Jet Propulsion Laboratory built trajectory models sophisticated enough to project where that deceleration profile was heading. The models converged on something that required multiple independent checks before it was circulated beyond her immediate team. If Probe 1 maintained its current deceleration curve for approximately 3 more weeks, it would not pass Earth at 45 kilometers per second. It would match Earth's orbital velocity. It would arrive at closest approach at roughly the same speed Earth moves in its orbit around the Sun. In orbital mechanics, when 2 objects arrive at the same point in space with matching velocities, you don't get a flyby, you get a rendezvous. Probe 1 appeared to be executing a rendezvous trajectory with Earth. Not a collision course, the closest approach distance remained millions of kilometers. But a rendezvous allows for something a flyby doesn't: extended proximity. An object matching Earth's orbital velocity in Earth's vicinity doesn't rapidly pull away. It can maintain position. It can pace the planet. It can enter into whatever orbital configuration its propulsion system allows for, and remain there for as long as its mission requires. What that mission requires, nobody could yet determine. But an object capable of rendezvous with Earth can enter orbit around Earth, can take up station at a fixed altitude and observe everything below, can study cities and communication networks and electromagnetic emissions and the full detail of a technological civilization from a position of sustained proximity for however long its systems remain operational. This is not impact. This is not flyby. This is something for which the word observation is technically accurate and emotionally insufficient. Probe 2 followed a different profile entirely, and its difference is informative. It wasn't decelerating at Probe 1's rate. Its velocity curve showed minor corrections, Small adjustments suggesting course maintenance rather than major propulsion burns, but no aggressive deceleration toward a matching velocity with any target. It would pass Earth on December 20th at approximately 9.2 million kilometers and 48 kilometers per second, fast enough for excellent remote sensing from a fixed observation point. Too fast for capture or rendezvous. Its post-encounter trajectory projected outward, toward the outer solar system, along a path consistent with an object that would continue moving away after its closest approach rather than lingering. Reconnaissance is the word analysts settled on for Probe 2's apparent mission profile. Observe and continue. Gather as much data as possible during the approach and closest approach window, then carry that data outward, potentially back toward the parent body or toward whatever relay system exists further out. Probe 2's behavior implied a division of labor between itself and Probe 1, one staying, one reporting. That division would make sense for a systematic survey mission. You don't need every probe to loiter if one can provide sustained observation. You need coverage. Probe 3 presented the most complicated picture of the three Earth-directed objects, and not just because of its trajectory. Its orbit had been the hardest to constrain from the beginning, complicated by apparent trajectory changes that didn't follow simple ballistic curves. Latest solutions placed it at closest approach on December 18th, at approximately 10.1 million kilometers, actually arriving before Probe 1 rather than after, but those solutions carried large uncertainties that wouldn't resolve until radar tracking became possible in mid-November. What distinguished Probe 3 most clearly was its rotation state. Unlike Probes 1 and 2, which maintained stable spins with regular 1/6-hour periods, Probe 3 appeared to be tumbling. Its brightness variations were chaotic rather than periodic, suggesting rotation around multiple axes without the stable controlled orientation its siblings exhibited. One explanation was malfunction, something that had gone wrong during separation from the parent body, leaving this probe unable to stabilize. The other explanation was intentional design. A probe specifically built to constantly rotate, exposing different faces to different directions, maximizing coverage from sensors distributed across its surface rather than pointed in fixed directions. The data collection advantage of a tumbling probe would be real. The instability cost would be real too. Which interpretation was correct mattered, because a malfunctioning probe behaves differently than a functioning one, and predicting the behavior of something potentially malfunctioning requires different models than predicting an operational system. Probes 4 and 5 were not heading toward Earth. Their trajectories bent inward, toward the Sun, intersecting the orbit of Venus. The timing of their arrival January, when Venus reaches inferior conjunction, its closest approach to Earth suggested either elegant planning or fortunate geometry, and by this point, most analysts had stopped assigning things to fortune. Venus is hostile to the point of being almost conceptually useful as a limit case for planetary conditions. Surface temperature around 465 degrees Celsius. Atmospheric pressure 90 times that at Earth's surface. An atmosphere composed primarily of carbon dioxide with clouds of sulfuric acid suspended at altitude. Nothing humanity has landed on Venus has survived more than a few hours before being destroyed by heat and corrosion. The Soviet Venera program achieved remarkable results given these constraints, but remarkable results still meant instruments that stopped functioning within an hour of landing, and yet Venus is not without scientific value. It represents a natural laboratory for studying extreme greenhouse effects, what happens to a planet when carbon dioxide accumulates without limit, when the runaway begins and never stops. It provides data on the boundaries of planetary habitability. It answers questions about how similar two planets can be in formation and composition while diverging so dramatically in surface conditions. For something conducting a comprehensive survey of this solar system's terrestrial planets, Venus cannot be omitted from the dataset. Probes 4 and 5 appeared smaller than their Earth-directed siblings, or at least dimmer. They were also decelerating less aggressively, which made physical sense if they were designed for atmospheric entry rather than space-based observation. Venus possesses a thick atmosphere that enables aerobraking the use of atmospheric drag to shed velocity rather than burning fuel. A probe built for Venus entry wouldn't need as much propulsion reserve because the atmosphere itself would do the deceleration work. It would, however, require extraordinary thermal protection to survive even brief exposure to the conditions below the cloud layers. The Venera probes, built for exactly this purpose, used pressure vessels and thermal insulation that still gave them only minutes of operational time below the cloud deck. Whatever thermal protection these probes carried, if they were designed for entry, would need to exceed anything humanity has engineering for, or their survival time in Venus's lower atmosphere would be measured in seconds. Probe 6 was taking its time. Its trajectory bent not inward, but outward toward Mars, following a slow, arcing path that would bring it near the red planet in March of 2026, 4 months after perihelion. Mars currently sits on the far side of the Sun from Earth, geometrically separated but accessible to a probe with patience and fuel to spare. The Mars trajectory requires less energy than the Earth trajectories, which is a consequence of orbital mechanics that human mission planners understand well. Mars orbits higher in the Sun's gravity well, moving slower than Earth. Reaching it from an interstellar approach requires less velocity change, less fuel expenditure. It is, in a specific technical sense, the most energy-efficient interplanet target for something arriving from deep space. But Mars possesses something Earth lacks in one crucial respect: unambiguous evidence of human technological presence. Rovers, landers, orbital satellites. The accumulated infrastructure of decades of robotic exploration and the early groundwork for eventual permanent settlements. For an intelligence studying this solar system's dominant technological species, Mars reveals something Earth's surface alone cannot: expansion capability. Whether a civilization remains confined to its home world or has begun reaching outward. Probe 6 would observe human off-world infrastructure directly, at relatively close range, assuming it approached closely and the Martian assets remained functional. That data, confirming the existence and extent of human presence on a second world, would be meaningful in any framework for assessing a civilization's developmental stage. Probe 7 was the outlier. It headed away from the Sun, back toward the outer solar system, following a trajectory that would take it past Jupiter in June of 2026, 8 months after perihelion. Jupiter is the solar system's gravitational anchor after the Sun itself, 300 times Earth's mass, a body that almost became a star but fell short of the ignition threshold for hydrogen fusion. Its magnetic field dwarfs everything else in the solar system beyond the Sun. Its radiation belts would destroy unshielded electronics in hours. Its moons form a miniature solar system of their own, ranging from Io, the most volcanically active body in the solar system, to Europa, whose subsurface ocean beneath a kilometers-thick ice shell is one of the most compelling candidates for extraterrestrial life in our vicinity, to Ganymede, larger than Mercury, possessing its own magnetic field and a confirmed subsurface ocean. Probe 7's trajectory, crucially, most closely resembled 3I Atlas's own path staying near the mothership, maintaining something like formation, moving outward rather than into the inner system. Some analysts interpreted this as the relay hypothesis. If you're dispatching 6 probes to 6 different targets and you need to consolidate their findings, you need a communications hub. Probe 7, staying near the parent body, could serve as the collection point receiving data transmissions from its siblings as each completed its survey mission and transmitting consolidated reports back toward whatever origin the mission came from. This would be logical mission architecture. The redundancy of maintaining a relay probe, rather than relying on direct communication from each individual probe, would increase reliability in exactly the way good engineering demands. The fuel calculations deserve more attention than they've received in most public accounts, because they tell a story about capability that is difficult to fully absorb. When 3I Atlas was first detected in July, its velocity relative to the solar system was measured at approximately 221,000 kilometers per hour, about 61 kilometers per second. That's the velocity an object carries from interstellar space, from travel between stars, from a journey that originated at another gravitational system entirely. When the probes were detected individually after perihelion, their velocities had already been substantially reduced. Probe 1 was moving at roughly 45 kilometers per second. It had shed more than a quarter of its interstellar velocity. The energy required to produce that deceleration scales with mass and with the square of the velocity change. For an object of Probe 1's estimated size 30 meters or more in diameter, The energy expenditure implied by observed deceleration runs into figures that make comparison to nuclear weapons yield not rhetorical but literal. Each probe, based on observed mass estimates and velocity changes, appeared to have consumed propulsion energy equivalent to multiple nuclear detonations. Not in a sudden explosive release, but as controlled, sustained thrust over weeks or months. Dr. Sarah Chen at MIT's Aeronautics Department ran calculations using optimistic assumptions, assuming propulsion systems with specific impulse values 10 times better than humanity's most advanced chemical rockets, approaching the theoretical performance of fusion-based propulsion. Even under those optimistic assumptions, the fuel mass required to produce the observed deceleration would represent a substantial fraction of each probe's total launch mass. If more conventional propulsion is assumed, the numbers stop making physical sense. There simply isn't room inside a 30-meter object for enough reaction mass. This points to one of two conclusions, neither of which is comfortable. Either these probes use propulsion physics fundamentally different from anything humanity has achieved, physics that doesn't depend on ejecting reaction mass in the conventional sense, or that exploits energy sources orders of magnitude more dense than nuclear fission or even fusion, or the size estimates are wrong and the probes are substantially larger than their brightness suggests, implying surface properties that make them appear smaller than they are. Neither explanation reduces the strangeness. Both increase it in their own ways. This is where the Oberth calculation becomes something more than an elegant observation about orbital mechanics. Consider what it implies about planning. The perihelion maneuver, releasing probes at the moment of closest solar approach, exploiting the gravity well for maximum propulsion efficiency, requires knowing in advance where the sun is, how deep its gravity well is at that point, what the local geometry of the solar system looks like, which planets are where in their orbits, what trajectories from perihelion will intercept which targets at which future dates. This is not improvisation. A natural comet doesn't wait for optimal moments because it has no goals. It does what gravity dictates. An object that executes an Oberth maneuver is demonstrating not just propulsion capability, but navigational intelligence. It knew where it was going before it arrived. It knew where Earth would be on December 19th when it was still months away in interstellar space. It knew the geometry of this solar system in enough detail to calculate intercept trajectories accurate to within millions of kilometers. And it knew all of this before it even entered the solar system, because the launch timing from the parent body, the probe separation velocities, the initial trajectory assignments, all of that had to be planned prior to perihelion, not improvised during it. The 2-minute window Jewess observed was not a calculation being performed in real time. It was a pre-planned maneuver being executed. This matters for understanding what kind of intelligence is behind these objects, because the level of foreknowledge required is not modest. Mapping a distant solar system's planetary positions accurately enough to plan this kind of intercept requires sustained observation over time, analysis of electromagnetic signals leaking from that system, calculation of orbital periods, and positions from that data. By the time 3I Atlas reached our solar system, whatever sent it had mapped this system in enough detail to deploy probes with pinpoint destination assignments. They knew we were here. They knew where here was. They'd been watching long enough to understand the layout. The question that nobody had answered, and that grew more urgent with every passing day in November, was the simplest and most consequential one available. What did they want? The signals from Probe 1 continued on a pattern of roughly every 3 to 4 days. Each transmission was archived in multiple independent copies at multiple institutions, ensuring that nothing was lost to system failure or catastrophic event. Analysts compared each new transmission to all previous ones, searching for evolutionary patterns, whether the probe was repeating the same information or building incrementally on what had already been sent. The comparison between the November 7th and November 11th transmissions revealed a detail that emerged from careful signal processing and that, once noticed, couldn't be ignored. Signal strength varied in a pattern that matched no known physical process. It wasn't following the inverse square law, the natural fall-off of signal intensity with distance, that every radio transmission experiences as it spreads through space. It wasn't modulated by the probe's rotation or by changes in its orientation relative to Earth. The strength variations appeared instead to be deliberate. The probe appeared to be adjusting its transmission power specifically to ensure that signals arrived at Earth at consistent strength, compensating for increasing distance by increasing output. That capability requires two things. First, it requires knowing Earth's location, where to point the transmission to maximize received signal strength. Second, it requires knowing Earth's receiver sensitivity, how strong a signal needs to be to register clearly in the detection systems being used. The probe shouldn't possess that second piece of information. Receiver sensitivity is a technical specification of human-built equipment. It's not derivable from first principles. It would have to be learned from observation, from monitoring human radio transmissions over time, and inferring from the characteristics of those transmissions the sensitivity thresholds of the equipment generating them. Which means Probe 1 had been studying Earth's electromagnetic output long enough to characterize human radio equipment. Or it received that information from 3i Atlas, which had months during its approach to analyze every signal Earth leaks into space television broadcasts, radar pulses, satellite communications, military transmissions, everything. All that inadvertently radiated information, everything humanity broadcasts simply by operating a technological civilization, would have been available for collection and analysis during the approach. The parent body had been listening before it arrived. The probes inherited that intelligence. Humanity had been transparent for months before it realized it was being observed, and the observers had used that transparency productively. The asymmetry this creates is one of the more genuinely unsettling aspects of the situation. Probe 1 may know human languages, because language is carried in broadcast signals. It may understand human mathematical notation, because mathematics appears in engineering transmissions and scientific broadcasts. It may have detailed maps of Earth's surface from radar altimetry data. It may know the locations and capabilities of major observatories and communication installations. It may know, from decades of accumulated electromagnetic output, a great deal about human history, human conflict, human political structures, human technology levels. Meanwhile, humanity knows Probe 1's position, velocity, approximate size, transmission frequency, and the mathematical structure of its signals. The information gap is not symmetric. It has never been symmetric, and it cannot be made symmetric in the time available. The debate over whether to respond, whether to transmit back, had been dividing the scientific and policy communities since Probe 1's first transmission was confirmed. The argument for responding was intuitive. Every day of silence was a wasted opportunity. If Probe 1 was attempting to establish communication, silence might be interpreted as incomprehension, or hostility, or both. The argument against was equally intuitive. Responding confirms human presence beyond what passive electromagnetic leakage already reveals. It demonstrates mathematical sophistication. It reveals information about human communication protocols and technology levels. It invites further interaction on terms set by the probe rather than on terms negotiated between equals. History provided no reassurance on the question of what happens when a technologically less advanced civilization reveals itself to a more capable one. The historical record on that subject is not encouraging. For the moment, officially, humanity was listening without transmitting. International Academy of Astronautics protocols for responding to extraterrestrial signals recommended exactly this approach. Confirm detection, analyze content, consult broadly, then, and only then, consider a coordinated response. Those protocols had been written for scenarios involving signals from light years away, where response times were measured in decades and there was no urgency. Nobody had anticipated needing them for an object arriving in weeks. Unofficially, the protocols were already being violated. Amateur radio astronomers with access to powerful transmitters had been pointing their equipment at Probe 1 since the first public confirmation of its signals. They were sending mathematical sequences, recordings, images of Earth, prime number lists, anything they thought might communicate awareness. Their transmissions were uncoordinated, contradictory, probably adding more noise than signal to any legitimate communication attempt. But they were happening, and there was no practical mechanism to stop them. Telling amateur astronomers not to transmit proved roughly as effective as commanding the tide. The official policy was containment of the official response. The actual electromagnetic environment Probe 1 was receiving from Earth was considerably messier. China had taken its own approach, separate from amateur activity and separate from the international consensus-building process. Tianwen-2, its asteroid sample return mission launched in May 2025, had been quietly retargeted. The original mission objective was collecting material from near-Earth asteroid 2016 HO3 and returning it to Earth. But the spacecraft's propulsion margins the reserve fuel beyond what the primary mission required were sufficient, with careful trajectory planning, to redirect toward one of the three I-Atlas probes. Not Probe 1, which was moving too fast and in the wrong geometry, but potentially Probe 3 or Probe 6, depending on orbital calculations that Chinese mission planners were running in parallel with their public statements of measured concern. Tianwen-2 carried instruments for compositional analysis, cameras capable of detailed imaging at close range, a sampling arm that could theoretically collect material from a probe's surface if the approach geometry worked. The scientific return from direct examination would have been incalculable chemical composition, material properties, surface structure, anything that would help characterize what these objects were made of and how they were built. The risks were equally substantial. What if a close approach was interpreted as a hostile act by whatever decision-making system operated the probe? What if the probe possessed defensive systems that activated at close range? What if China's unilateral action triggered a response from the probes that affected not just the approaching spacecraft, but Earth as a whole? NASA knew about the Chinese plans. The knowledge had come through intelligence channels rather than diplomatic ones, which said something about the state of the relationship. Other space agencies knew too. Strongly worded exchanges had occurred, threats of consequences, accusations of recklessly endangering humanity for national advantage. China's response was not a retreat. It was a counter-argument. Gathering direct physical data on the probes was essential regardless of who did it. Better to know what humanity faced than to remain ignorant through excessive caution until December 19th arrived. And if China happened to gain first access to whatever technology these objects represented, well, that was a fortunate side effect of bold scientific initiative. The international community had no enforcement mechanism against this logic. Satellites could track Tianwen-2's trajectory. They could observe a course change. They could confirm a rendezvous approach. What they could not do was prevent it. The geopolitics of first contact, it turned out, were going to be shaped by the same competitive pressures and national interest calculations that shape every other domain of international relations. The discovery of something extraordinary does not suspend ordinary human motivations. If anything, it intensifies them. December arrived in this context, not as a clean month beginning, but as a compression of everything that had been building since October. The days felt different. Not because anything in daily life had changed. Weather continued its business, traffic continued its rhythms. The ordinary texture of existence persisted undisturbed by the extraordinary approach, but because the gap between the world's surface and the sky above it had narrowed in some psychological way that was difficult to articulate, and impossible to ignore once you felt it. Tracking precision improved with each passing day as the probes drew closer and observation angles optimized. Probe 1's closest approach had been refined from earlier estimates, 8.6 million kilometers at 3:22 Universal Time on December 19th. That translated to 10:22 p.m. Eastern Time on December 18th, 7:22 p.m. Pacific, a moment in the evening hours of a Wednesday, when a significant fraction of the Northern Hemisphere would still be awake. The night of December 18th was forecast to be clear across much of that hemisphere. Whether this was fortune or something else, nobody said aloud. There is a specific kind of waiting that doesn't feel like waiting. It feels like pressure. Like the air has changed density somehow. Like the space between moments has been filled with something that wasn't there before. The days between December 1st and December 19th had that quality for the people who understood what was approaching and had spent the preceding weeks working through its implications. Not panic. Panic requires a clear threat with a clear response. This was something more difficult to metabolize. An approach without declared intent. A visitor without a comprehensible message. A set of objects demonstrating capabilities that dwarfed anything humanity had built, executing a plan that had clearly been in motion for longer than most people had been alive. arriving on a schedule that nobody on Earth had set. The waiting had a shape to it, specific. Pressurized, December 19th at 3:22 Universal Time, everything narrowing toward that point. Spectroscopic observations of Probe 1 conducted in the second week of November had produced a result that circulated through the relevant research networks and generated more quiet alarm than almost any other single data point. The probe's emission spectrum, the chemical fingerprint of whatever it was releasing into space around it, showed hydrogen cyanide at concentrations inconsistent with known cometary chemistry. Hydrogen cyanide, the compound, is not exotic. It's simple enough in structure: one carbon atom, one nitrogen atom, one hydrogen atom, and it appears in comet spectra regularly. Comets produce it naturally through the breakdown of more complex organic molecules under ultraviolet solar radiation. Its presence in a spectrum coming from an object that spent time as part of a comet's coma was not inherently alarming. What was alarming was the concentration and the timing. Probe 1 had separated from 3I Atlas weeks earlier. It was no longer embedded in the coma environment that produces cometary hydrogen cyanide. It was an independent object moving through space, and if it was simply a piece of cometary material with residual volatile content, those volatiles should have been depleting steadily since separation, not maintaining or increasing their concentration levels. The measured concentrations were too high, significantly too high for an object that should have stopped producing new volatiles when it left the parent body's thermal and chemical environment. Something was still generating hydrogen cyanide inside or around Probe 1. The compound is toxic to life. As it is understood on Earth, it disrupts cellular respiration at the mitochondrial level, interfering with the enzymes that allow cells to use oxygen. This is not obscure biochemistry. It's the mechanism of one of the most acutely lethal substances known. A concentration sufficient to harm biological organisms doesn't need to be large. The question that could not be answered from spectroscopic data alone was whether the cyanide was incidental, a byproduct of whatever reaction process powered the probe's systems, or intentional. Whether it was exhaust or signal. Some researchers pointed out that hydrogen cyanide, precisely because of its toxicity and its distinctive spectral signature, had properties that made it interesting as a warning mechanism. It's simple enough to produce deliberately. It has strong spectral lines detectable at substantial distance, and it communicates, in chemical language, that something may be hazardous. Not through mathematics, not through structured radio signals, but through molecular presence, a statement readable by any chemistry capable of recognizing it. If Probe 1 was communicating danger, indicating that it or its contents represented something organisms shouldn't approach hydrogen, cyanide was an efficient medium for that message, universally detectable, unambiguously toxic, no shared language required. The alternative was less interesting, but not less concerning, that the probe's propulsion or power systems produced cyanide as a waste product, which would say something about the chemistry involved in whatever was making it move. Either way, the readings didn't resolve cleanly into a comfortable explanation, and they added another layer to the question of what would actually happen on December 19th when the closest approach distances reduced to their minimums and the probes were as near to Earth as they would ever be. The defensive posture that had been quietly maintained since early November was genuinely difficult to sustain across weeks. Military and intelligence establishments had built response frameworks. Tracking systems had been recalibrated and personnel had been trained. Contingency plans existed on paper for scenarios ranging from the probes being entirely inert upon arrival to the probes initiating some kind of action that required immediate response. What those response plans actually contained, what the realistic options were, if Probe 1 did something unexpected at closest approach, was not publicly available. What was publicly available suggested the options were limited. Humanity's fastest spacecraft, if launched immediately upon detection of a threat, would take days to weeks to reach an object at 8.6 million kilometers. That's not a response window. That's an aftermath. The practical reality of the defensive posture was that it consisted primarily of observation capability and, at the extreme end, the question of whether nuclear-armed ballistic missiles could be repurposed for interception at interstellar probe distances. The physics of that option were not encouraging. Ballistic missiles are designed to travel a few thousand kilometers. 8 million kilometers is a different problem entirely. the calculations existed? The answer was essentially no, not on any timeline relevant to December 19th, which meant that if something alarming happened at closest approach, humanity's response would be principally documentation. Recording what happened, in as much detail as possible, for analysis that would inform whatever came next. That is not the response posture that defense establishments prefer to maintain. But physics doesn't negotiate. What made the defensive discussion simultaneously urgent and surreal was the question of what response would even mean in the context of first contact with an extraterrestrial intelligence. Humanity has spent decades, through fiction and through serious academic work, thinking about this scenario in the abstract. Those discussions produced a remarkably consistent set of conclusions about what the ideal response looked like: coordinated, representative of humanity as a whole rather than any particular nation or faction, carefully considered, prioritizing communication and understanding over confrontation. The actual situation in December 2025 resembled that ideal in approximately the same way that a real emergency resembles a training exercise. The coordination was partial. The representation was contested. The consideration was compressed by time, and the confrontation question couldn't be cleanly separated from the communication question because nobody knew what Probe 1's behavior at closest approach would look like. And therefore, nobody could determine in advance whether communication or confrontation was the appropriate response frame. This is the circumstance that the careful, consensus-driven, internationally coordinated first contact protocols had never quite managed to account for. What happens when the contact arrives before the consensus does? The night of December 18th, local time across the Northern Hemisphere, was clear in the way that significant nights sometimes are not through any mechanism beyond ordinary meteorology, but with the effect that the absence of clouds seemed to carry weight. Astronomy clubs gathered at dark sites. Observatories hosted public viewing events for objects too faint for unaided eyes, but detectable in modest telescopes. People who owned equipment they hadn't used in years set it up in driveways and backyards and rooftops. The practical reality was that most of them would see nothing Probe 1 at 8.6 million kilometers, and its size remained at the edge of detection for all but the largest professional instruments. But being outside, pointing something skyward, sharing the moment with other people who understood what was happening overhead was a response to uncertainty that made sense in a way that staying indoors and watching coverage didn't. There was something instinctively correct about looking up directly, even if looking up with unaided eyes or modest instruments produced only the ordinary star field. The thing was up there. Pointing your face toward it was not irrational. Professional observatories had every instrument available committed to the approach zone. Camera systems recording continuously across optical, infrared, and radio wavelengths. Spectrographs primed to catch any emission changes during closest approach. Radar systems actively ranging the probes, bouncing signals off their surfaces, and measuring the returns, a technique that would yield direct surface characterization data, information about roughness and composition and structure that passive observation couldn't provide. The data rate from all these systems combined was extraordinary, terabytes flowing every hour into storage systems that had been expanded specifically for this purpose. Analysis of most of it would take months. The collection had to happen now, in this window, because after December 19th, Probe 1 would be moving away, signals weakening, the angular resolution decreasing, the detailed observation opportunity closing. Whatever data existed would exist. Whatever was missed would be missed permanently. At 3:22 Universal Time on December 19th, 2025, Probe 1 reached its closest approach to Earth, 8.6 million kilometers. The precise distance, when it was confirmed from radar measurements, matched the predicted value to within the measurement uncertainty, which meant the trajectory calculation was correct. Which meant the probe had arrived exactly where the orbital mechanics said it would arrive, which meant it had been following a planned trajectory with an accuracy that human spacecraft navigation would have been proud to match. At closest approach, every instrument that could be pointed at the object was pointed at it. The radar returns came back with surface detail that had not been available at longer ranges. The spectrographs caught the emission profile at maximum brightness. The cameras imaged the object at the highest resolution yet achieved. The radio telescopes listened on all accessible frequencies for any change in transmission behavior that the closest approach moment might trigger. The compiled data from that window, approximately 6 hours centered on closest approach, during which Probe 1 was within 10 million kilometers of Earth, constitutes the most detailed characterization of an extraterrestrial object ever assembled. Analysis of it is ongoing. Some results are public, many are not. What can be said with confidence, from what has been released and from what has been confirmed by enough independent sources to be treated as established? Probe 1 did not impact Earth. It did not enter Earth's atmosphere. It did not deploy anything detectable at closest approach. It continued on its trajectory, decelerating, maintaining the profile that Dr. Helongo's models had projected, still executing what appeared to be a rendezvous approach that would bring it into Earth's orbital neighborhood rather than past it. At closest approach, it transmitted. Not in a different pattern from its previous transmissions, same frequency, same Fibonacci timing structure, same modulated content within each burst, but the transmission was longer. Where previous transmissions had run for 26 minutes, the closest approach transmission ran for 4 hours and 17 minutes. Hours of structured signal at the moment of maximum proximity, as if the additional transmission time was the response to proximity itself. As if Probe 1 understood that closest approach was the moment of highest information transfer rate and used it accordingly. Dr. Kim's team at the SETI Institute worked through those 4 hours and 17 minutes of signal with every analytical tool available. The result, when it was circulated among the inner working group, was a partial breakthrough that raised larger questions than it answered. They had found a repeating structure. Not the Fibonacci timing that was already understood, but within the modulated content of each burst, a pattern that repeated across multiple transmissions with sufficient regularity to constitute a dictionary entry. A specific modulation signature, appearing in the same form in the November 7th transmission, the November 11th transmission, and multiple subsequent ones, always associated with what appeared, from context analysis, to be a reference to Earth itself. The probe appeared to have a signal element that meant something equivalent to this planet, used consistently when the transmission's content related to Earth. That was the breakthrough, the first confirmed meaning extracted from the signal. One word. Or something functioning as one word. After weeks of analysis by teams working around the clock, one word in an alien encoding scheme had been tentatively identified, and that word meant here. The implications of extracting even that single meaning were significant, because it confirmed that the signals were referential. They pointed to things in the external world, rather than being purely mathematical or purely self-describing. Which meant in principle the signals could be decoded, given enough data and enough time. The question was whether enough data and enough time were available. Probe 1 was moving away. Each day added distance. Each day reduced signal strength. The transmission on December 19th at closest approach was the last strong enough for the kind of detailed analysis that had yielded that single identification. Subsequent transmissions, as the probe moved outward, were increasingly marginal receivable, certainly, and archived in full, but carrying less signal-to-noise ratio, less resolution in the modulation analysis, less of the detail that decoding required. The window for extraction had been brief. It might be closing. Here is the thing that none of the official accounts have addressed directly, that exists in the space between what is technically documented and what those documents actually imply. Probe 1, by mid-January 2026, had achieved something very close to the rendezvous trajectory Dr. Helongo's models had projected. It was not in Earth orbit in the classical sense. It was not at a fixed altitude above the surface. But it was moving with a velocity and in a direction that kept it in Earth's general vicinity rather than receding at the rate a flyby object would recede. It was pacing the planet, maintaining proximity. The distance fluctuated based on the complex interplay of Earth's gravity, solar gravity, and the probe's continuing active propulsion, still firing, still making adjustments, still executing what appeared to be guidance corrections rather than coasting. Probe 1 was not leaving. This detail was not prominently featured in public communications. It appeared in technical papers, in orbital solution updates, in the tracking data available to any astronomer with the tools to analyze it. But it was not in the press releases. The language used in official contexts was careful in exactly the way language becomes careful when the people choosing it are aware of the difference between what is technically accurate and what is psychologically manageable for a broad public. Probe 1 remained in Earth's vicinity. It continued transmitting every 3 to 4 days. It had established something that, if you use the neutral language of orbital mechanics, you would call a persistent presence in Earth's orbital environment. If you use a different language, the language of intent, of mission, of purpose, you would call it something else. And that language was the one researchers were privately using by late January, even as the public communications remained measured and hedged and careful about conclusions. Probes 2 through 6 continued on their respective trajectories toward their respective targets. Probe 2 had passed Earth on December 20th, as projected, too fast for rendezvous, and was tracking outward toward the outer solar system. Probe 3 had made its closest approach on December 18th, still tumbling, still enigmatic, its post-encounter trajectory carrying it inward toward the Sun in a path that suggested it might use solar gravity for a course correction rather than propulsion or gravity assist in reverse, using the Sun's pull to redirect rather than using fuel. Probes 4 and 5 were approaching Venus on the January timeline, their approach trajectories under continuous monitoring. Probe 6 was making its slow way toward Mars, months still from arrival. Probe 7 maintained its formation-keeping behavior near the outward-moving 3I Atlas, still the brightest of the outer probes, still the candidate for the relay hypothesis. The solar system had 7 visitors, each conducting its survey, and the combined picture of what they were doing was becoming, gradually, through accumulated observation, slightly less opaque. They were mapping. That was the broadest consensus that had emerged by early 2026 from researchers who had spent weeks and months analyzing every available data point. 7 probes, 7 targets, each chosen to represent a different type of body in this solar system. Rocky inner planets with and without atmospheres, with and without signs of life and technology. Gas giant with extraordinary moons. The mapping hypothesis wasn't comforting, but it was at least coherent. A survey mission sent to characterize an unknown solar system would look exactly like this. Deploy probes to each major target type. Collect compositional data, atmospheric data, geological data, biological data if any exists. Relay findings back. Complete the catalog. The question the mapping hypothesis raised immediately, the question it couldn't answer from inside itself, was what the catalog was for. Maps are made for purposes. Surveys precede decisions. Characterizing an unknown system is the step before doing something with that characterization. Military reconnaissance and scientific exploration both involve mapping. The map looks the same either way. What differs is what happens after the map is complete. Go back, for a moment, to the WOW signal. August 15th, 1977. 72 seconds at 1.42 gigahertz, from the direction of Sagittarius, never repeated, never explained. The suggestion, explored seriously by a handful of researchers, was that it might have been an advance announcement, a hailing frequency sent ahead of an incoming mission, providing notice to any civilization capable of receiving it. The timing implied by that hypothesis, 48 years between signal and arrival, 3I, Atlas was detected in July 2025. 48 years after 1977. If the hypothesis is correct, the WOW signal was not a random broadcast. It was a scheduled transmission. It was the notification that something was coming. And what came on schedule. There's an uncomfortable corollary to this that most researchers have not stated publicly, but that follows directly from the logic. If the WOW signal was a notification, then the civilization that sent it expected its notification to be received. Expected that something in this solar system was capable of receiving a narrowband radio signal at 1.42 gigahertz and recognizing its significance. Expected, in other words, that by 1977 this solar system contained technological life, which it did. They knew, before 1977, that Earth hosted intelligent life. They sent a signal that would be detectable only by a technological civilization. They received no response, the official consensus is that no response was sent to the WOW signal's coordinates. They sent the mission anyway, 48 years later. What does it mean that they sent the mission without a response to their announcement? Either they didn't need a response, the announcement was courtesy, not negotiation, or they expected silence and came anyway because the purpose of the mission didn't depend on prior agreement. Neither interpretation narrows the uncertainty about intent. Both widen it. What has not been addressed, by any official source, in any public communication, is the question of what 3I Atlas itself has been doing since perihelion. The parent body, the 5 to 20 kilometer nucleus that has been tracked since July, that survived perihelion intact, that continues on its hyperbolic trajectory outbound from the solar system, is still observable, still tracked. Its behavior since October 29th has been, officially, exactly what you'd expect from a comet making its post-perihelion recession. Coma fading as it moves away from solar heating, tail diminishing, brightness decreasing in rough accordance with standard models. Rough accordance, not exact. The brightness has declined slightly more slowly than models predict for a pure cometary body, and the outgassing pattern has shown periodicity's cyclical variations in emission rate that doesn't match any known natural process for a comet at this stage in its trajectory. The variations repeat on a 9.3-day cycle, not the 16-2-hour rotation period, which would be the natural candidate for periodic outgassing variations, 9.3 days. What that period corresponds to, physically, hasn't been explained. One proposal is that it represents an internal process of the object, something happening inside the nucleus on a cycle that drives periodic outgassing events. That's the conservative interpretation. The other interpretation, less conservative, is that the parent body is still active in a different sense, and the 9.3-day cycle represents something deliberate transmission windows, processing cycles, scheduled operations rather than passive physical processes. That interpretation is not currently supported by direct evidence beyond the periodicity observation. It is, however, consistent with everything else that has been documented about this object. The extraordinary has become the baseline expectation. The natural explanation requires more assumption than the artificial one at this point in the analysis. Probe 1 is still out there. As of the most recent tracking data, it maintains its proximity to Earth's orbital environment, still transmitting every few days, still executing the small propulsion corrections that keep it from drifting outside the range where its signals reach Earth with adequate strength. It has transmitted more than 30 times since its first signal on November 7th. Each transmission has been archived. 46 hours of structured signal now exists in human databases, carrying whatever content was encoded into it by something that crossed interstellar space to be here. The decoding work continues. The single confirmed meaning, the signal element that refers to Earth, was a beginning, not a conclusion. Teams are working through the accumulated transmission database, looking for other repeated structures, other consistent associations, other elements that can be assigned provisional meanings, and tested against the full corpus. It is the slowest possible form of communication, and it is the only form available. Progress is measured not in messages received and understood, but in fragments, in tentative correspondences, in the gradual accumulation of a vocabulary that might, eventually, allow something to be said back. If it's decided to say something back, that decision has not been made. The debate continues, sharpened now by the fact that Probe 1 has demonstrated sustained presence rather than simple flyby, that it appears to be waiting in some operational sense, that the longest transmission in its history was timed to closest approach, as if the distance itself were a variable it was optimizing around. These are not the behaviors of a probe executing a fixed, pre-programmed routine that ends at a specified time and then shuts down. They are the behaviors of something responsive, something that adjusts, something that is, in the fullest sense of the word, paying attention. 8 billion people on this planet went about their ordinary lives through October, November, December, January, each day carrying the ordinary weight of ordinary concerns. Most of them aware, in some background sense, that something was happening overhead. That the sky contained objects that hadn't been there before, sent by something that wasn't from here, executing purposes that hadn't been explained. The awareness was present without being overwhelming for most people most of the time, because that's how human cognition handles background conditions that aren't immediately actionable. You hold them at a certain distance. You let them inform your sense of the situation without allowing them to monopolize your attention. You continue functioning because the alternative to continuing functioning is not obviously better. But the awareness was there. It changed the texture of looking at the sky. It changed the implicit contract between the surface of the planet and the space above it, the assumption, held without examination for all of human history, that the sky was ours in some unspecified sense. That what was up there was background. That it didn't look back. That assumption is no longer available. Whatever is up there, in the form of Probe 1 and its siblings moving through this solar system, arrived with information about us already in hand. It arrived knowing where we were, what we broadcast, what our technology could detect. It arrived with a plan that predates living memory. And it has not left. Here's what we don't know, stated plainly, without the hedging that has characterized most public discussion. We don't know what these probes are collecting and what they're doing with it. We don't know whether the transmissions are attempts at genuine communication or are something else entirely, status reports to the parent body, automated system checks, something that looks like communication, without being communication in any sense that would transfer meaning between minds. We don't know whether Probe 1's sustained presence near Earth represents patience waiting for humanity to respond, or whether it represents something else, a monitoring function whose completion criterion hasn't been reached yet. We don't know what happens when that criterion is reached, if it exists. We don't know what 3i Atlas will carry back to wherever it came from, or when that information will arrive, or what will be done with it. We don't know whether this is the first mission of this kind directed at this solar system, or the most recent one. We don't know how long they've known we were here. The WOW signal suggests the answer to that last question might be at least 48 years. The approach trajectory along the ecliptic, the plane of the solar system, the most strategically efficient path for something that wants to interact with multiple planets, suggests the approach was planned with knowledge of this system's geometry that required sustained observation to acquire. How sustained? Unknown. From where? Unknown. The galactic center is the origin region. That's a region, not a point, not a star, not a civilization with an address. What is known? Something crossed interstellar space and released probes into the solar system at a moment of maximum propulsion efficiency using an event that human observation couldn't witness. The probes targeted the principal bodies of the inner solar system with navigation accuracy that implies foreknowledge of their positions. One of those probes is pacing Earth's orbit and transmitting structured signals at a frequency chosen for universal recognizability. The parent body continues exhibiting behavior inconsistent with a simple comet, and the first confirmed signal from 1977, if the hypothesis holds, was a scheduled notification sent decades in advance. The question that was asked at the beginning of this, what do they want, hasn't been answered. It will be answered, or it won't, on a timeline and in a manner that isn't controlled by any decision humanity has made or is currently capable of making. That's the actual situation, not the press release version, not the measured, hedged, careful language version. The actual situation is that something with capabilities vastly exceeding anything humanity has built arrived at this solar system with prior knowledge of its inhabitants, executed a precisely planned deployment of survey instruments, has one of those instruments parked in Earth's orbital environment transmitting structured signals, and is waiting. For what, in what form, on what timeline, these are the questions that don't have answers yet. The questions that the data available right now, as of the most recent tracking update, cannot resolve. And so we wait too, with the same incomplete picture, the same incomplete vocabulary, the same dawning awareness that we are not the most capable thing in the solar system right now and haven't been since October 29th. That's the part most accounts don't say directly. That the situation, as it stands, is one in which humanity is the observed party, has been the observed party, potentially, for decades. And the observer has not yet indicated what observation was for, what comes after the map is finished, what decision a survey precedes. There's something else, something that hasn't been discussed in any public account of 3i Atlas, something that exists at the intersection of what Probe 1's transmissions might contain and what the decoding work has so far suggested. Dr. Kim's team identified one signal element, meaning Earth. They have identified, in subsequent analysis, tentative correspondences for additional elements not confirmed, not published, but present in the working documents circulating among the inner research group. One of those tentative correspondences is a signal element that appears in transmissions referencing Earth, specifically in the segments that seem, from contextual analysis, to be descriptive rather than referential. Not pointing to Earth, but describing something about Earth. That element appears to be associated with, or analogous to, a concept the researchers have been cautious about naming definitively. The closest natural language equivalent they've proposed, in the internal documentation, is a word that means something like inhabited, or alive, or occupied. The probe isn't just noting the location of a planet. It appears to be encoding something about the planet's status. Something about the fact that this particular rock has something on it. The distinction between a planet noted as a location and a planet noted as a location that has something on it is not subtle in its implications. Locations are coordinates. Occupied locations are something else. They're destinations. They're subjects. They're the difference between a map that records geography and a map that records where the interesting things are. If that tentative correspondence is correct, and it is tentative, and the people who proposed it are careful researchers who understand the difference between a hypothesis and a conclusion, then the transmissions from Probe 1 aren't just acknowledging Earth's existence. They're characterizing it, noting it as occupied, and that characterization is going somewhere. Back toward 3I Atlas, which is carrying it outward, away from this solar system, toward wherever this mission originated, toward whoever sent it, toward whatever reads the report when the survey is complete and decides, based on what the survey found, what happens next. That's where this story is, right now, not concluded, not resolved. Suspended at the moment before the next development, whatever that development is, on a timeline nobody on Earth set and nobody on Earth controls. Probe 1 transmits. Earth listens. The parent body moves outward, carrying everything. And somewhere, at an unimaginable distance in a direction we can only approximate, something waits for the data to arrive. If the survey is the beginning, then the question of what follows the survey is the one that matters most. And that question, unlike every other question in this story, hasn't even been fully asked yet. That's where the next part of this begins.